In Chapter 11, we talked about whether molecules were polar or nonpolar, and that helped us decide if two things would mix together. And we use that rule, like dissolves like. When you get to larger molecules, though, sometimes it's a little unclear whether your molecule is polar or nonpolar, because sometimes big molecules will have polar groups, like this carboxylic acid over here, and then nonpolar groups, like this long carbon-hydrogen chain. And so then we have to ask ourselves, okay, is this going to dissolve in a polar or a nonpolar solvent, if we think about our rule, like dissolves like? And basically what we need to just decide is, okay, is this molecule more polar or is it more nonpolar? So we look at whether it has more polar groups or nonpolar groups, and then just kind of round up or down. So in this top example, we see that we only have this one carboxylic acid group down here, and then this molecule has this really long hydrocarbon chain. So overall, this molecule is probably more nonpolar than it is polar. So this is more likely to dissolve in a nonpolar solvent. If we look at this butanoic acid, however, we can see that it has this big polar group and then a pretty short hydrocarbon chain. So overall, because half this molecule is polar, this is probably going to be more soluble in a polar solvent. So all you got to do is identify polar and nonpolar areas. The nonpolar areas are going to be your parts with a bunch of hydrogens and carbons. Polar areas will contain oxygens, nitrogens, or other nonmetal atoms. And sort of round up or round down, is it more polar or more nonpolar? So these are usually pretty easy. We can look at a quick example here. Determine if each organic molecule would be more soluble in water or hexane. Now the reason they use these two is water is just sort of the universal polar solvent, and hexane, we can see it's all carbons and hydrogens, so it's usually considered pretty much the universal nonpolar solvent. So it's just another way of saying polar or nonpolar. So what we can do for each molecule is just look at how many polar groups it has and then decide if we're going to round up to polar or down to nonpolar. First example is caffeine. If we look, caffeine has a lot of polar groups. Got a lot of these oxygens here, got several nitrogens, and so because it has all these polar groups, we're going to round this guy up to polar, even though he does have some nonpolar groups as well. Because of that, we're going to say water is going to be the solvent it would be more soluble in. And that makes sense because we know caffeine is in a lot of water-soluble, or is in a lot of drinks containing water. Coffee, soda, they all have water as the base, and we know caffeine is dissolved in there. All right, other example, we see here vitamin D. Let's look for our polar groups, and we see it really just has this one down here, and everything else is just a lot of carbons and hydrogens. We should recognize this part, that's some organic line structure there, just represents carbons and hydrogens. So overall, this has primarily nonpolar groups, and so it's going to be more soluble in hexane. It does have this one little polar group here, but most of the molecule is nonpolar, so we're going to round down to nonpolar and say it will dissolve in hexane instead of water.